Hi everyone, this is Dr. Nally. So this is the second video related to the ideal gas equation where we'll derive an equation for gas density. So the topic of gas density is a little separate from the ideal gas equation just because we want to talk specifically about how we can write the ideal gas equation to solve for density. And of course you remember from our discussion on density in chapter 1 that density is mass over volume. So if you want to derive an equation for gas density, it has to be solved for this expression of mass over volume. Okay, and let me do that now on the next page. So to derive an expression for gas density is fairly straightforward. We're going to start with our PV equals nRT, which is our ideal gas equation. Remember that I wrote it more as PV over RT, PV over NT equals R, the constant, but you can, this is the usual way you guys would see it written. And of course we want to solve for mass over volume because that's what density is. So in other words, we need to somehow express one of these terms in terms of mass because we eventually want to take the mass and divide it by volume. And if you remember, number of moles, of course, which is N, is just mass of a substance divided by its molar mass times RT. So that allows me then to write it in this form of the equation. And if I separate the M and the V together as a fraction like this, which is what density is, then what I should get is, of course, PM over RT, and this is the expression for the density of a gas. Okay, again, this only works if you were talking about gases, right? So we're not talking about solids or liquids. In this case, we're just talking about gases because gases, you can measure its pressure and temperature easily, and then R is applicable to gases only. Okay, going back now to the slide, I mentioned here that you can, the density of gases is useful because you can usually determine it from experiment by measuring the mass of and volume of a gas, and from there you can use that, as you can see, related to the molar mass of the gas, which is shown here. So a lot of times it's useful information, the density, because you can use that information to then figure out what is the molar mass of a known gas, for example. Okay. In general, as we've talked about before, gases are a lot less dense than solids and liquids. You'll see why when we get to the kinetic molecular theory of gases, because a lot of gases are just empty space. So you usually see that in terms of units, the gases are about 1,000 times less dense than corresponding liquid or solid version of that same substance. Okay. So now what I want to do is just work a fairly simple problem of calculating density of carbon dioxide here at 0.99 atmosphere and 55 degrees Celsius. So remember that we just did it in the previous slide, how to we derived this equation or this expression for the density of a gas, which is just P M over RT. And we basically, it's just a matter of plugging this particular numbers, the information you have, into that equation. So you have 0.99 atmosphere. You have a molar mass, which in this case of CO2 will be just 44 grams per mole. That I get from the periodic table. R is 0.0821 liter atmosphere in this case over mole Kelvin. And then lastly we have temperature, which of course in this case has to be expressed in Kelvin. So then we have 55 plus 273 Kelvin. And if you look out at all the units, they should cancel out to give you the appropriate units at the end. You see what's left is grams and liter, grams per liter, and that's a unit of density, of course, mass over volume. So if you were to actually make that calculation, you should get a value that's 1.618 grams per liter. One thing I want to point out, of course, here is the idea that the density of this gas is fairly low in comparison to a corresponding liquid or solid. So for example, here's the density of the CO2 in the gas form, grams per liter. if you look at the density of solid CO2, which is of course what we also call dry ice, you'll find that the density is around values of 1.5 grams per milliliter. And as you can see, there's a lot more mass, per a much smaller volume in this case. So it's a lot more dense in comparison to the gas. So that's something to pay attention to as far as the density of gases in comparison to the density of the condensed phases, solids, and liquids. So in the last part of the video here, I just want to show you a little bit of a demonstration of how density of gases affect their ability whether to float or to sink in air. If you remember, we talk about these type of experiment with water, for example. You can tell whether an object is more dense than water or not by whether it sinks in water versus when it floats. You can do the same with gases by comparing it with air. For example, if you know the density of air is to be a certain value, then the density of these gases can be compared to air, and you can do an experiment where you see if the density is lower, then the balloons will float up, whereas if the density is higher, then the balloons will sink or would actually go to the bottom. Okay, and this short video will basically demonstrate that particular experimental observation.
Here are 5 of the 6 noble gases: helium, neon, argon, krypton, and xenon. They're all colourless and transparent. Krypton and xenon form compounds only with difficulty. Helium, neon, and argon don't form compounds at all. As we descend the group in the periodic table, the atomic number and the relative atomic mass increases. The gases get denser. Helium is lighter than air. Neon is just lighter. Argon and krypton, I've just got to unstick these from the anchorage for a moment. Argon and krypton are both heavier than air. And xenon is the heaviest of the lot. You've heard of a lead balloon? Well, this is it.
Okay, so hopefully that would show you a little demonstration of how you can use the principle of density, in this particular case density of gases, and compare it to density of air around you in terms of balloon, and see which ones would float and which one would actually sink to the ground.